Okay, welcome back everyone. So we are starting our panel discussion. So we have 5 talks, each will be 12 minutes hopefully, and then followed by a 30-minute discussion where audience can ask questions. So at the end of the talks, let's not have Q&A, so hold your questions up until the end for the panel discussion. And the first speaker is Harchol from Carnegie Mellon University. Let's welcome.
So thank you. I'm very honored to be invited to be here. I'm from the computer science department at Carnegie Mellon, but I really consider myself a LIDS person who happens to live in a computer science department. And you'll understand that through my talk. So as you can see, I work in the area of queuing theory, and I'm often standing there in the airport wondering why there's this very long line in the women's room, and there's no line in the men's room. I feel a lot better, by the way, at conferences. But at airports, I'm very disadvantaged. And I wonder about this. And The Economist actually did a whole study on why there are lines in the women's room. And the reason they came up with is that women spend twice as long in the women's room on average as compared to men. Okay, I don't know, hand washing, things like that, whatever, but they spend twice as long. And it causes long lines, okay? And so one of the things that they said was, well, maybe what we need to do is double the number of women's rooms, and maybe that will, clear up the problems. But we as queuing theorists know that that's not actually enough. Doubling the number of women's rooms will still not be enough. So let's go and take a look at a little bit of queuing theory. So I'm going to start by talking about traditional queuing models. And the simplest queuing models is just a single queue. Okay, you can imagine people queuing up. I think of this as a router queue or a buffer queue, a run queue for the CPU, where jobs are queuing up, and then there's a server where they get served. A little bit more complicated is the kind of queue you see at a bank. So you have a queue, and you have a bunch of servers, and whenever a server is free, it grabs the next person to work on. So whenever the server is free, the next person is run. So this is another type of queuing system. Another kind of queuing system is like the queuing system you see in a supermarket, or you see this in a data center. It's the dispatching kind of queuing system, where there are a whole bunch of separate queues, and then there's a front-end dispatcher, which is, say, sending each person or each job to join the shortest queue. So you're joining the shortest queue. So these are standard traditional queuing models. We spend a long time analyzing them and stuff. But you might ask yourself why there are queues to begin with. I mean, why do we even have queues in computer systems? Isn't everything very fast? One of the questions I get asked a lot by companies is they say, well, we don't even understand why we have queuing because our utilization is pretty low. The load is pretty low, okay? There aren't that many arrivals compared to the service rate. So why is there so much queuing going on? Okay, and the answer is the queuing usually comes from the variability in your job sizes. It's not so much a function, I mean, of course it's a function of the load, but the variability in your job sizes counts just as much. And so you can have low load, but still have high variability, and that creates queuing. And I want to talk about what that looks like. Okay, before I talk about it, I just want to point out, in all of these models, a job, what I call a job, occupies one server and one server only. And I'll come back to this point. Okay, so why we wait? So if you look at today's computer workloads, and I'm going to give you a graph, an arbitrary graph from a typical company that I would talk to, okay? On the y-axis here, I have the probability that the job size exceeds x. And on the x-axis, I have x CPU hours. So I'm using x as the size of a job, the number of CPU hours. And the typical graph that I see on a log-log scale looks kind of like that, okay? Basically like a straight line. So you start here at the top, that's all jobs, and then the fraction of jobs decreases, decreases, decreases as you get to bigger and bigger jobs. So the first thing you notice is there's this huge range of job sizes. When I'm talking about variability, I'm really talking about variability. The squared coefficients of variation that I'm measuring today are well over 1,000. This is very different from what I learned in my textbooks of squared coefficient of variation of 1, okay, that many of you have learned too, all right? We're talking well over 1,000. But it's worse than that. There is an extremely heavy tail. So when you look up on Wikipedia, like what is this heavy tail thing? Like what does it mean? What they say is, oh, it's the 80-20 rule. 20% of the jobs make up 80% of the load. That is not correct, okay? Forget that. Forget that you heard that. So let's just take a look at that in the graph. Suppose I look at the top 20% of the jobs, okay? What you see is this yellow line there. That's the top 20% of the jobs. But this is on a log scale. So that yellow space, that 20% of the jobs, are actually waking up way, way more than 80% of the load, basically 100% of the load, okay? Almost 100% of the load. What you really want is you want to look at the top 1% of the jobs. And it turns out, unbelievably, that the top 1% of the jobs make up 97% of the load, 97%. So if you look here at this top 1%, it looks very little, this little yellow line. But this little yellow line on a log scale is 97% of the CPU cycles. Just to try to put it in perspective, you all graduate from MIT. You're very smart. Maybe you're in the top 1% of the richest people in the United States. Suppose you take that 1% richest people, okay, this top 1%, and you say they control 97% of the money. Okay, that's the kind of numbers I'm talking about. I'm talking about 97% of what's going on, made up by 1%. And this has huge implications for scheduling. This is the heart of the problem. These 1% are hogs. They're resource hogs, okay? Some people call them elephants. I call them hogs. They're eating up everything, okay? And everybody else, 99% of the jobs are blocked behind them. And that's what causes delays. So when you go back to queuing and you try to understand, okay, what's happening here with this 1%, you'll see a lot of the research that people do today and have been doing is really on better scheduling. And I myself spend a lot of time working on better scheduling to combat job size variability. How can we manage to get the short jobs to not get stuck behind the long ones? Okay? What if we don't know the size of the short jobs? How do we get things to jump ahead of the long ones? That's some of the research. Other research is also dealing with job size variability. Like, how do we do better dispatching to maybe separate out queues for short jobs and have separate queues for long jobs so that short jobs don't get stuck behind long jobs. And this is a big problem, is this variability, and that's why we're dealing with it. Okay, but that's all in the past. If you go back here and you look at my previous slide here, every single job is occupying one server only. In today's world, it's a parallel world, and our old queuing models are no longer right, okay? And all of us who work in queuing, like myself, are scrambling to catch up. So if you look at today's systems, a data center might be 10,000 servers easily, okay? That's one cell of a data center. Okay, your desktop is 16 cores. Your laptop is multiple cores. Your cell phone has multiple cores, okay? Everything we're dealing with is a multi-core, multi-server system. And today's jobs no longer run on one server. They run on multiple servers at the same time. And we as queuing theorists have to figure out what does that mean in terms of how we're going to understand their delay. So let's think about this. A job occupies many servers. Let's take a look. So here's the system I showed you before. But now when a job comes in, it needs multiple servers. Here I'm saying 2, it might be 2,000, okay? Next job comes in, it needs some number of servers, okay? And it's going to occupy them and hold on to them for the whole time that the job is running. The next job's also a parallel job. It needs some servers. More and more parallel jobs arrive. Hello? Okay, next one. Maybe a job arrives here, a size 2 job, needs 2 servers. Should we let it jump ahead of the 3s or not let it jump ahead? These things aren't so obvious, okay, what you should do. But not only do we not know what are the best strategies here for minimizing delay, we really don't understand delays in the setting at all. And the setting gets even more complicated when the jobs have tasks, and the tasks, instead of all running at the same time, take different amounts of time. So when the individual tasks take different amounts of time, and now the job isn't done until all the tasks are done, things get even more complicated. So these are the kinds of problems that in the queuing theory world we're now working on. Really, the problem comes in a more complicated setup where a job might need some number of compute resources and some number of memory resources. So here's the next job. It needs some compute and some memory. Next job comes in. It needs some compute and some memory, but it doesn't fit. So it has to queue. And again, we are interested in understanding what are delays like in settings like this. Okay, now some of the research that I've been doing most recently has gotten even more complicated than this. Not that I understand how to do this yet, okay, but it's become more complicated because I've been talking to people in machine learning. In machine learning, the jobs are not only parallel, but they're often malleable. So what I mean by a malleable job is that it is flexible as to how many servers it can run on. It doesn't have to run on 4 servers. It can run on any number. So let's take a look at this. Malleable jobs. The job is flexible in the number of servers that it needs. So again, imagine a job coming, and a job looks like a block. And this job could be run on 1 server, or it could be run on 2 servers, or it could be run on all the servers. Why not run it on all the servers? Depending on how many servers you run it on, you get a different speed up. So you can see this is what I call perfect speed up, this line here, where if I run on 2 servers, I run in half the time. If I run in 3 servers, I run in a third the time. Like, life is good. Reality's not so good. Reality looks more like that. Okay, so now, okay, if I just have 1 job, sure, I might as well give it all the servers. But suppose I have a second job, and it has its own speed up function. I have a third job, and it has its own speed up function. How do I decide how many servers to allocate to each job? I might decide, for instance, that I want to give the yellow job most of the servers because it's the short job in the spirit of shortest jobs first. But this is the kind of LIDS type calculation when we're talking about doing the theory. This is the type of calculation that we have to do to try to understand what we should be doing here. And not only is it an open question to decide how many servers to allocate to the jobs, but it is also an open question to understand what the delay will be like once we implement those kinds of algorithms. So in summary, it's a parallel world, and there are a lot of exciting new queuing theory problems. I hope you've learned something about queuing. Thank you.
So our next speaker is Mike Neely from University of Southern California.
You know, in reflecting on Moore's talk, I realized something. First of all, how do I do? Which is the laser?
Oh, a laser.
Okay. So I realized for your 1% queuing problem, I think Bernie Sanders has written a bill to solve that problem. Elizabeth Warren has a plan to solve that problem. So I'm Mike Neely. I'm a student of Eitan Modiano from LIDS, and I'm going to talk about a classical problem of fairly allocating transmission rates in a multi-user wireless network. So the problem setup is a very simple one I've drawn here. Oops. So here we have 3 users, and we have to make a decision about who transmits. So we can look at the current channel states and say, well, this looks good, so I'm going to choose that particular user because he has a currently good channel state. But the difficulty is we don't know what's going to happen in the future. And we don't even know the probability distribution associated with what's going to happen in the future. But somehow we want to optimize some utility function of the time average rate vector of all of the users. It's a vector because it's multiple components. So as time goes on, we see some channels. OK, maybe I select this one. Maybe I select this one, and so on and so on. So a general algorithm is going to look at what has happened in the past in terms of the channel states as well as the decisions, and then make some decision that hopefully is efficient for the current time step. So how can we think about this? Well, there's a famous algorithm for doing this. So one idea is to keep some kind of a time average of the transmission rates. And so this x average of t is a vector of time average rates that we've accumulated over time up to time t. And there's different kinds of time averages that you can have. So there's some step size eta t. It's not clear immediately how to choose this step size, but let's assume that we're choosing it somehow. We're creating some kind of a time average. Then on the current slot, we can look at our current set of transmission rate options, which is determined by our current channel conditions, and then make a decision for the rate vector now that maximizes an inner product of the transmission rate vector now with the gradient of the utility function evaluated at the time average. So I'm assuming that we have a smooth utility function that I can take the derivative with. And this was, actually, there's a LIDS connection because David Shea has done some work on this problem early on. And then there was some follow-up work later where people were looking in a fluid limit sense and analyzing the efficacy of this. There's another LIDS connection. I talked with Subramaniam about this a few years ago, and he said the inspiration for this, it's called a Frank-Wolf type scheduling. He said his inspiration was in reading a section of a book on deterministic Frank-Wolf by Dmitry Bertsikis. Well, I would still like to understand this problem more. In particular, well, some questions that follow up this work are, well, does this really work? And how long does it take to learn to make good decisions? That's a fundamental question that goes beyond this particular example to any kind of learning. Yeah?
You said theory always works.
Oh, okay. Well, that's the answer. That's going to be the answer to this question. So you get 10 points for. So I'm interested in convergence time and also adaptation time. And in particular, what step size should I use? Should I use a running average, where essentially the step size is diminishing over time, or use a fixed step size, which represents some kind of exponentiated average? And this itself is also a fundamental question in other areas of optimization, where you might have some step size. How do I choose the step size? So here are some recent results in this direction that partially answer some of these questions. Well, it turns out if you use a running average, that's the step size going to zero like 1 over t. You can show that the utility you get is greater than or equal to the optimal utility that you could have even if you knew the future, minus a term that decays to 0 like log t over t. So that's good. You get optimality as time goes on. And furthermore, log t over t is optimal. So in fact, a year ago, I didn't know if I could remove the log, but I've been able to show recently, you can actually show a converse that says no algorithm can do better than log t over t. But that's not necessarily good. So the question is, do you want this optimal algorithm? But it is optimal, but at what cost? Well, I'm going to show you that something that I call the adaptation time of the algorithm is in fact infinity, which is the worst that you could possibly have. Essentially, I'm going to define adaptation a bit more clearly in a simulation that I show. But essentially, you can see that if you're having a step size that goes to 0, you're making increasing investments in a particular probability model that you are learning over time. If that probability model itself changes, how long is required to unravel the previous time averages that you've already been accumulating? Well, it depends on how long you've been accumulating it, and in fact, it can be an infinite amount of time, or arbitrarily large, I should say. On the other hand, if you use a fixed step size, you can show that you also go to optimality, but it's a lot slower. And you can even see in the simulation that it's a slower speed. So it still goes to optimality. The convergence time is suboptimal. However, you can show that this now can adapt when the system changes. So let me show you a quick simulation. Here's this algorithm in green, which is using the running average. So it's computing an average starting from time 0. It has a vanishing step size. It's extremely quick. In fact, we can prove it's optimal. It very quickly, okay, so this is a 50-user system. I'm only plotting the performance of user 1. This horizontal asymptote is the steady state optimal transmission rate on average that user 1 should get if it does things in an optimal way that maximizes the utility function. But I'm running over 4,000 slots, and I'm going to change the probability distribution in the middle, but I'm not going to tell the algorithm that I changed the probability distribution. It just has to learn that. And so this horizontal line is what it should converge to for the new steady state. So you can see when you start out, we're telling the algorithm we're starting now. So it can converge very quickly. The green line is very, very fast to the optimal. But when I change, you can see it takes a very long time to reach the new steady state. And in fact, if I just scale the time, make 4,000 into 40,000 and 4 million slots, then I can make this time get as arbitrarily large as I want. So that's why I say the adaptation time, which is reacting to an unknown change somewhere in the middle of the simulation, is in fact arbitrarily large. So you can say, well, okay, well, let's use the fixed step size. Then maybe that solves the problem. So here's a fixed step size with 1/100 step size. That sounds pretty small. In this particular case, when we start out, it actually converges to something that's not so bad, and it's also very quick. But then it converges again much more fast, but it converges to something that's kind of far away from the true optimality. So there's a cost in going to something that's adaptive, and that is the quality of the solution. And now if you increase the step size further to get that quality up, that's this one. So now the step size is 1/1,000. You can see even starting off, it takes some time to converge. And then here, it takes a longer time to adapt. So let's see. Now you can also ask, well, wait a minute, why not just use, since I know the running average is optimal, why not just use a running average starting at 0, but just periodically restart? And you can show fundamentally that doesn't work. So here I'm restarting at time 1500. If I knew that the change was going to be at time 2000, I would just restart at time 2000. But since I don't know that, you can prove that that's not a solution to this problem. You still get the fundamentally worse adaptation time. In fact, these adaptation times to get an epsilon approximate solution are 1/epsilon squared. And that turns out to match a larger class of algorithms that can solve more difficult problems that I call the drift plus penalty algorithm that I started working on in my thesis. Those are adaptive, but they can't get the convergence time speed of the run algorithm, but they don't make these increasing investments in a particular model. So the open questions are, well, we can define now the optimal convergence time, but is there an optimal adaptation time that we can prove? I think this is more interesting to a broader class of learning problems. How fast does it take to learn something to make a good decision? And then what are the things that we need to learn? What sufficient statistics are there? How do we map to estimation problems and so on? And so what algorithms are involved, and can we get improved converses? So I think these are kind of interesting open questions. And that's the end of my talk.
Thanks a lot, Mike. So our third speaker is Muriel Medard from MIT.
Thank you. Thank you for inviting me. I figured I would start with what I thought I knew when I had graduated as a PhD student from Bob Gallagher's group here. And basically, this is what I thought I knew. Okay, I thought you start with data, you squish it. That source coding, you then expand it because it goes through the channel. We heard quite a bit about all the fundamental contributions to channel coding that so many people in this room have made. And then you keep going like that, and it's sort of the Krebs cycle. And I felt pretty sure about that. So I thought I knew how to do this. You started out basically by expressing the mutual information between the input and the output. And the first part here, that h of x, was the first part where you squish the data. So that's how much information you had. And the second part was the uncertainty that came from trying to estimate the data by just looking at the output. So the first part was the compression, the second part was the channel, and I was like, okay, this is good. I'm just going to work on this. We're going to maximize, and off we go to the races. Okay. So the problem, of course, is this doesn't take delay into account. This is just the throughput. And one of the things that actually we were discussing the other day at lunch with Erdal, one of the things that I think is interesting, was interesting to me, is to what extent the expectation of the inverse is not the inverse of the expectation. Now, I'm sure to everybody in this room, this was obvious. It was a surprise to me. I knew it, but just to the extent to which it's not is amazing. So in effect, the delay, delay which is the in-order package delivery delay versus the maximum delay, which is how long it takes you until you finish, until you've given everything to the receiver, is actually massively, massively different. And in particular, what this means is if I'm looking at something which is going to require something fairly real-time, say Skype, versus something where you're having, or maybe like a rateless code or something will do because you're really just looking at throughput, you have this very, very strong kind of like Pareto optimum curve between whether you're coding really just for throughput or you're coding for delay. And I think that this sort of trade-off between throughput and delay, which is particularly important as we're looking, everybody's heard about 5G and low latency communications and so on. I think that this kind of trade-off is something which I hadn't anticipated, certainly as a graduate student, and now I'm doing a lot of work, and obviously many people also in this room are working on. So basically, what came out of looking at all this was that this is something fundamental, and it's even more the case when you're looking at a network. So for instance, if you're looking here at having a multi-hop network with several relays, it's really the same throughput that I can have on either side by encoding, decoding, re-encoding, decoding, and so on, or just by doing recoding. And whether I have feedback or not, frankly, it doesn't matter from the point of view of throughput. But the behavior in terms of delay is entirely, entirely, entirely different. And so this effect of really having to it's not that you're really getting more throughput and therefore getting better delay, that you're going to have to trade off one for the other. You have to pick which one you get. It's something that definitely was surprising to me. So at this point, I realized that I didn't know that. Okay, that wasn't what I was trying to do. I wasn't trying to maximize this reliable throughput and this mutual information. I was like, okay, well, maybe that's not what I was trying to do. Maybe I should have been thinking about the delay. But let's just stick with this. At least I feel I know. Remember, the first term corresponds to the compression, the source coding. The second term corresponds to how much I'm losing versus the information that's in X because of the uncertainty that comes from the channel. So let's see what I can do with this. Let's see if I can at least work with this. So, again, just to remind ourselves, here's the data after the compression, and I'm going to lose something in effect because of the channel uncertainty. So basically, I start out with this h of x, and I like this little cartoon here. For you, many of you recognize this type of cartoon. But basically, the idea is, what is the entropy? And of course, the idea here is that people may take very, very complicated passwords, and they're not necessarily more difficult to guess than it does here. And of course, here they're looking at entropy. They really mean H, like Shannon entropy. Now, again, I knew about Rényi entropy, but I hadn't really thought of it as being something very important. And I think many of you here will be aware maybe of the work that started with Massey, and of course that Erdal Arikan so massively contributed to. And actually, this is really just a refinement of one of Erdal's works from the 1990s. But basically the idea is if I look at the guesswork here, which is, how long is it going to take for me to guess the password that I just showed you, it's actually not related to the Shannon entropy. It's really related to the Renyi entropy of order 1/2, plus some other terms that come in here, some log terms. Now, why that matters is because really, for instance, when I'm worried about whether somebody is going to break my password or not, it's not the Shannon entropy that matters. They're likely to break the password if I have some very likely passwords, or else if it takes them a long time, it's because we're looking at the very unlikely passwords. Okay, and therefore this Renyi entropy here is going to be higher than the Shannon entropy because it's a really rare passwords that take a long time to guess. It's basically weighted more towards the unlikely events. So at this point, I realized that I also didn't know quite what the entropy was, and maybe I should be rethinking the entropy. Therefore, as it goes along, obviously I'm learning less and less, or I know more, or at least I'm learning that I know less and less. So the idea here is now, if I look at this mutual information again, the second term, as I said, corresponds to what I lose because of the estimation error through the channel. And the one thing I also did think I knew was that if I wanted to go to higher rates, this would take more work. Somehow, it just seemed, not just what we saw empirically, but also it seemed right that if I'm going to get more throughput, I should be paying for it through blood, sweat, and tears. Okay, let me review what I thought I knew, which was this entropy of h of x given. Remember I had written it in the way I used to think about it, but I can rewrite it, of course. As everybody in this room knows, I could instead rewrite it as the entropy of the output minus the entropy of the noise. The room is full of coding theorists. I don't need to tell you that this is basically what the syndrome is doing. The syndrome is taking the noise and compressing it. Let's go back to the password that we saw before. What was so funny about that password? Well, what was funny about that password is I told you, really what's dominating there is the really unlikely passwords because of that Renyi entropy. But the likely passwords, I'm likely to actually guess very quickly. That's why people manage to break into password-protected systems, okay? So then, what I should do is I shouldn't be trying to do this in this way. I shouldn't be compressing the noise because I've taken out all of the structure of the noise. If I want to really look at the noise, I should be keeping the structure. I don't care about the really unlikely noise. I'm never even going to guess it because I'll be making an error before I get to that. And just to give you some idea there, here's some very recent work that we've been doing trying to actually implement this. And this is, I keep referencing Erdal, but that's because this is using polar codes, which have made into 5G standard for control channels. So these are those polar codes with some additions, with LIDS decoding and some CRCs. And all I wanted to show you is this is how it does to guess the noise when I have LIDS decoding. This is with a list of size 32. So this is using this polar codes with CRCs. And this is how I do with hard decoding and with symbol reliability aware decoding and with soft decoding with very, very low complexity. So basically, at this point, I think, I'm knowing less and less, but at least I'm aware of it. I think at this point we're down to X. Okay, the entropy gone, the mutual information, how I was going about it gone. So at least I have X, so this is it, find X. Well, you can imagine, I also don't know this, because, when I thought of X, and again, thinking just in terms of, remember X, this H of X was, the compression, that was sort of like the information, right? It's a self-information that's in the random variable X. And there I felt like, okay, I know obviously what H of X is. It's not very enticing, but, things are distributed. We heard Moore speak about how everything is distributed now. What does it mean for me to have my data distributed? when I'm looking at source coding. Well, there's Wiener-Ziv, there's Slepian-Wolf. You can generalize it to arbitrary networks. We did this with my former student, Tracy Ho, and others. And if I want to do this, however, when I'm looking not at x, but at a function of x, it's quite different. It's quite different. Why? Because the identity, which was x, is a function, but it's the identity function, which is like not the most interesting function out there. And therefore, what will happen in particular is that my capacity regions, remember I started out thinking that you start by compressing and then you send it. I don't actually want to send x. I actually want to send just enough rate for you to be able to recover the function that you want to compute out of x. So that's what I actually know right now, but at least I'm really sure of this. Okay.
Thanks a lot, Muriel. So our fourth speaker is Emre Telatar. I already introduced him.
So this one I haven't really put too much thought into, honestly. Plus, I mean, people who know me, they know that I'm email phobic. So I must have received emails about what the format of this panel was going to be, but I completely was unaware of it. So that's why there's probably slides and so forth. I saw this as a panel, we're going to talk, but there are slides. So I wasn't sure what to talk about. There were things that I sort of knew, things I know a little bit that I could talk about, but I'm taking a bit of a risk to talk about things I don't really know about. So with this caveat, but I think I'm among family and friends. I'm back to my intellectual home. So I think I can embarrass myself and not take a huge risk here. Voilà. So this is more of a let E be a Polish space kind of talk. And then it's 4:45. I think only at MIT one can sort of do this kind of stuff. You show up and say, okay, at the end of the day, we'll start with a Borel field. But so here's, but I'd like to draw your attention to the date and the name. This is about networking, but in 1976, I'm not really sure what kind of networks were there. I think Aloha was recently invented. So the idea of what a protocol is, etc., were really very much up in the air. But somehow I think Bob had gotten wind of these things and decided to do some interesting work on them. So, so here is, suppose you have some kind of a network. The network accepts packets and delivers them at the other end. So AIs are the times when the packets arrive to the network, when the packets are accepted, and DIs are the times when the packets depart from the network, when they're delivered to the destination. And you want to ensure that the network behaves well in the sense that it puts a guarantee on the amount of delay that these packets suffer. So the difference between the DI and the AI, if you average them out and take their expectation, this number should not be too big. You want to put a guarantee of this particular type. And for convenience, let's assume that the arrival is a Poisson process. Okay, why not? Okay. So now, the fact that you have put this delay guarantee between the arrivals and departures essentially says that the two processes, AI and DI, cannot be independent. Because had they been, you will not be able to say anything about the differences between the Ds and the As, which means that consequently there must be some positive correlation, some positive mutual information between these two processes. And consequently, even if the packets had no content at all, if the packets contain no data whatsoever, your communication system, your network, your whatever it is, has to provide provision capacity to meet the delay constraint. So these kinds of guarantees on the performance impose costs on the infrastructure. You have to provision additional capacity to guarantee that these delay constraints are met. Now the question is, how much? Right. Okay. I have very few slides, so I can talk a lot about each slide, but I still run out of time, I'm sure. Okay, so how much? And the answer is given by this particular thing, okay? It is a lower bound. You need to provision at least this R of lambda d. Remember, lambda is the arrival rate, d is the delay that you guarantee. And this number is like something like minus log lambda d if lambda d is small, and e to the minus lambda d if lambda d is big. So this is no big deal. This is a small number, okay, if lambda d is large. Namely, if the delay guarantee that you provide is much bigger than the inter-arrival time between packets 1 over lambda, you don't need to worry about too much. But if it is the other way around, this can be significant. And maybe in this, given the morning's talk on all these automated driving and so on and so forth, you may want to be interested in getting data fairly quickly to where it needs to be, because if you don't, your car is going to climb a tree or something, right? So you don't want to do this. Okay, so that's sort of one encounter between the information theory and networking-like concerns. Another one is a similar type of problem, perhaps in a dual. This is from the mid-90s by Venkat and Sergio. So what you have is the following. So packets arrive to a exponential time server queue. The queue is initially empty. The packets are injected at times A1, A2, etc. And then the packets depart this queue at times D1, D2, etc. And the packet I takes SI amount of time and so on and so forth. I'm not even sure why I wrote these equations. But the question I want to ask is the one that's on the bottom. What can you say about how much mutual information is there between the arrival and departure processes? And the answer to that also can be given in a fairly nice enclosed form. It has to do with the log of lambda over mu, okay? So rather mu over lambda. So mu is the service rate, lambda is the arrival rate. If you feed the queue with an arrival rate that is faster than mu, you get nothing. This plus sign means that if this number is negative, take its positive, make it to be 0. But if lambda is less than mu, then you can make the mutual information is upper bounded by this log of mu over lambda. And amazingly enough, it'll in fact be equal to this if AI happens to be a Poisson process. So if you feed the queue with a Poisson stream, you get in fact the maximum possible mutual information. So in some sense, this is the capacity of the queue in terms of timing information. So this is not about the packet delivery, but how much information are you conveying to the receiver through the arrival times of the packets. And if you convert this thing in terms of, this is essentially in terms of per packet, this makes it to be per unit time. And if you now try to optimize this thing or a choice of a lambda, you'll choose a lambda to be about 1 over e times mu. Okay, that's this, and there you get that. Okay. Now, something else which is much more recent has to do with the concept of age of information. I'm very grateful to Tony Efremidis, who's sitting in the audience, for popularizing this particular topic. And the topic is perhaps due originally to Roy, who's also sitting over there. So my apologies to both of them for talking about something which they own, but I hope they'll forgive me and making a hash of it. So the observation is the following. Even if there is no delay at all, suppose this delay is 0, it doesn't mean that the information is timely. Because in between the arrival, the departure of these packets, the person sitting at the receiver is unaware as to what is happening at the input side. Your information is getting stale. You received some packet at some particular time t, so say di, and as t increments between di to di plus 1, your information is getting stale. T minus AI is the timestamp of the packet that you last received when it was generated. So this is the age of the information. If you take a look at what is the age evolution, you will see that this is something like a sawtooth function. And what you can find is you can figure out what is if you take a exponential server queue again, and the first in, first out queue discipline, you can figure out what is the average age, what is the time average value of the sawtooth function. You'll find it in this particular strange expression there, and you can now try to optimize this over the arrival rate lambda, namely how often should you sample the process that you wish to monitor to get the lowest possible age. You'll find it to be some particular value, happens to be at some strange 0.53 blah blah number there. But now, based on these things, this particular one can perhaps ask a more Gallagher-like question in here. Suppose you have some random process, u, discrete time, which you wish to monitor. Okay? About this random process, you deliver something to the monitor itself, which is v. So v is what you deliver to the monitor, okay? Subject to some causality constraint, namely that the v's that you create up to time I, if you condition on the process itself up to time I, they should no longer depend on the future of the process to be monitored. So your system is not cheating and looking to the future. Okay? And then also you take a look at the VI here, and then you say, things that I've seen up to VI at the monitor, what can I say about the input process? What is the latest time j in which I know the value of u sub j? Okay? So what is the j comma uj, which I can predict from observation vi? Let this largest value of j to be ki. So this is the freshest information that you have at the monitor. And then the question that I want to ask is, this is then your average age. At time I, you know about things at the time ki. This difference is how old is your information. This is your average age, versus how much mutual information needs to be between the u and the v processes. So for example, if you now connect some information and a monitor by a channel of capacity c, it'll upper bound this, which will then lower bound the age by some rate distortion-like function. Now it turns out, even at the simplest possible instances of this question, say u to be a IID Bernoulli process or something like this, these ends up being extremely difficult to say anything about. Okay? So there is some very curious math which happens here. So this could perhaps be something of interest to a LIDS kind of crowd. So just want to say these things, although I guess there is much more fancy things that we could really say, talking about polar codes or connecting information theory and machine learning, etc. All these things are also possible topics, but this is something that is, I think, cute and simple, but maybe we may want to be aware. So thank you.
Okay, now our final panelist is Erdal Arikan from Bilkent University in Ankara.
Thank you very much. So I was Bob Gallagher's student from 1981 to 86. I left early in January 1986. I came to MIT to do information theory, hoping to do information theory with Bob. Unfortunately, at my first meeting, he said the remaining problems in information theory are either too difficult or not too elegant. Nevertheless, I ended up doing some information theory as my PhD thesis. My MS thesis and also my PhD thesis were both on multiple access channels, and most people at the time in the communications group was doing multi-access of one type or another. Eli Gafni, he was my office mate. He was the senior person in the office. I remember Janine Mosley. She had developed a new multi-access algorithm, and we were all talking about the first come, first served splitting algorithm, and previously the Kapitsanakis 3 algorithm. So for us, it was very important to be able to improve the throughput of those algorithms by 0.1 bits per transmission, etc. Over the years, I developed a broader perspective of communications engineering, so I would like to present you my personal perspective. So I will begin with the past, and I will include the Shannon heritage, the 1950s, 60s, as part of the LIDS history, LIDS heritage. So in the beginning, MIT was the center of information theory research, 1950s and 60s, and many present coding techniques were invented then. at MIT or by MIT alumni in the later years. For example, product codes, convolutional codes, sequential decoding, LDPC codes, threshold decoding, concatenated coding, Burley-Campbell algorithm, Viterbi decoding. We owe all of these to the golden age of information theory at MIT. And these books are still the classics in the field. I regard them as books for eternity. So before I came to MIT, I had already taken some courses in information theory. The Wozencraft-Jacobs book was our textbook at Caltech. And we had followed a different information theory book, not this one, McDeese's book. But I was familiar with this book too. So information theory, the hope that I could study with Bob was my main reason for coming to MIT for graduate study. I don't know if you can read, but the book at the very bottom there in chronological order is Fano's Transmission of Information. And then you have the concatenated coding book by David Forney. So jumping to 1981, reading about the history of LIDS, I understand the agenda had changed over the years. And by the time I became a student at LIDS, the agenda was data networks. Network algorithms for routing, distributed algorithms, fair resource allocation, congestion control, and multi-access algorithm. And one other big issue was to integrate voice, data, everything in one network. So that was the dream, and I'm going to come back to it. Eventually, we were able to integrate it. When I say we, I mean the community. So I took data networks course from Dimitri Bertsekas, and a couple of years later, this book appeared. So within about 10 years' time, an interdisciplinary, a multidisciplinary area had taken shape, thanks to this research agenda, which I wasn't really very familiar about, because a graduate student doesn't really have a perspective. You think that the problems that people are doing are the most important problems, and that they are going to remain important. But that's not the case. So anyway, after I left MIT, I followed what went on at MIT for a while. And I know that all optical networking was another major research area. And then it was followed by, or perhaps simultaneously pursued with wireless communications. And I regard Emre's contribution to multi-antenna communications as also a continuation of this wireless communications research at MIT. So looking back, LIDS, and looking more generally, LIDS has been a pioneer of ideas. This morning, John, he gave a detailed account of it, a complete account of it, and it's very, very impressive. So many sophisticated ideas were developed at MIT and LIDS, and they are now part of modern communication systems and data networks. MIT researchers, they had the foresight to develop the theory, the algorithms, and also the architecture several decades in advance. And a prime example of this, it has also been mentioned, is the LDPC codes. They have become the workhorse of Wi-Fi, 5G, and they are here to stay. So looking into the future, or looking at the present, what are some of the forces which are shaping the communications industry and research in communications. I find it useful to define this notion of data sphere, which you see in the figure. It consists of three parts. There is the endpoints, which are the sources of data, and also the consumers of processed data. Actions are applied at the endpoints. Data is collected, they originate at the endpoints, and then they are consumed at the endpoints. There is the core of the network, which consists of the core network, the transmission system, the backbone, and also increasing the clouds, storage, processing, and so on. And between these two, there is the edge of the network. In particular, there is the wireless edge. And it's important to understand this architecture, the data sphere, to project the future of communications. So what happens is, at the core, data gets moved around, it is stored, and it is processed. At the edge, the endpoints and the core meet each other. And now problems are becoming severe, more challenging because of the immense growth in data. We all know about this. So this is creating a bandwidth problem at the edge because data has to cross the edge to get into the core, to get processed, to get disseminated. So wireless resources are limited, which means increasingly we are going to be challenged at the edge. And the backbone capacity, although it is mainly fiber, it is also going to be stressed. Furthermore, because most of the data is now real-time, for real-time applications, low latency, ultra-reliability are important for real-time control applications. There are also the data processing challenges, but they are outside the scope of what I want to say here. So the solution that the communications industry presents to us is the vision which can be summarized by this triangle here, the 5G vision of the future of communications, at least in the near term. At the top corner, we have the enhanced mobile broadband, more of the same, and then we have massive machine-type communications and ultra-reliable communications. So 5G proposes to provide all of these services by one single user interface. Looking forward, it is unclear if this is going to be possible. So to speculate, I have the feeling that we are going to see, instead of integration, which has been achieved, perhaps a disintegration of those services, because the core, just a single network, is not going to be able to provide these various different services, which differ from each other by service requirements, which are very different. So there is talk of network slicing, network function virtualization, and all of these things. So that's going to occupy our agenda. So I want to end at a positive note for communications people. I think there is a lot more things to be done. We will see increasingly more sophisticated networking and information theoretic ideas put into real systems. And with that, thank you very much.
All right, I wanted to thank all the excellent speakers. I learned a lot, and I think we were very fortunate that they shared their wisdoms with us. So now we can finally ask the questions, which I hope you accumulated over these 5 talks, actually 6 talks. So yes, please.
Sounds sort of some criticism, but I think it's relevant, especially if LIDS is going to be under the College of Computing. In my mind, in the 20th century, there were 2 revolutions associated with the word coding. One revolution is Shannon, and his revolution of coding was the interpretation of coding as reliable transmission of information from one point to the other. But there was another revolution in my mind of the word coding. And people use the word coding also to transmit from one point to the other without some adversary in the middle listening and understanding what you know. And this revolution was understanding that coding has nothing to do with some magic and enigma machine or whatever, understanding that this has to do with complexity, with solving, with the apparent impossibility of solving a complex problem. So, if LIDS has the word information, why we didn't adopt also that this should be an area of research? When Erdal says that transmission from point to point, it will not be transmission from point to point of clear code, of clear cipher. It will be transmission of something which was encoded against malicious. Who says that there is no big correlation? I mean, that you can serve on the total end-to-end by combining the two. When David talked about the blockchain and he says security, he didn't say that it doesn't mean security in the information theory meaning, but rather it's all under LIDS cryptographic. It's cryptographic against polynomial computing. Why don't we adopt? I think cryptography fits directly into LIDS.
So maybe, I don't know, this is a question to panel. I mean, I'm happy to provide my answer.
I think many of us can talk to that. I mean, as you said, sort of in the 70s, there's this bifurcation between the information theoretic security, sort of the Wiener wiretap, et cetera, and then more the computational approach, which is like the Diffie-Hellman approach, and sort of categorizing. It's a very broad taxonomy. But I think there's a lot of work at the intersection of the two. And I mean, I was talking about passwords there. Obviously, there's a lot of information theoretic work on those sorts of aspects. But I think there is a lot of work at the intersection. It's I'm sure many people here would. So I'm in agreement. but I think that bifurcation from the 70s, I think we're seeing a lot more convergence, I would say, over the last 5-7 years.
I think information theoretic secrecy suffers from architectural problems, simply because if X and Y are independent, namely you secure the X from somebody who knows Y, if X and Z are independent, you secure X from somebody who knows Z. It may not be the case that the Y and Z together, they may actually be infer X. This non-modularity of the security, I think, makes the problem extremely difficult to tackle. And I think unless we get some handle onto what are the correct architectural principles to understand security, it'll be difficult to make fundamental progress. I think information theoretic models, you can solve a whole bunch of toy settings and then say, this is the secure capacity of this or that communication model. But the real practitioners seem to completely ignore all we say. And I think it's not because they're idiots and then we have the correct answer and they don't understand us. I think it is because that we haven't quite found the correct models to say what we want to say about. Your point is extremely valid, that this should be an issue that we should be working on. But I think the work that we've done is actually very significant.
Can I make a point on that question? I think it's a great question. So I think historically, Shannon's first paper was on information theory of secrecy. Yes, that's information theoretic security. One of the first paper on computational secrecy that you mentioned is actually in the Transactions on Information Theory. Diffie-Hellman is a 1972 paper in the Transactions of IT. At a risk of simplification, I think it was a big mistake for the information theory community to let that branch of work go to a different field.
Okay, any other questions?
Bob.
Oh, Bob.
All of the research that seems to be going on now in the communication field seems to take as given that our function is to take whatever anyone wants to transmit and convey it to wherever they want to transmit it to. And people have commented about how difficult this is getting because there's a growing and growing and growing amount of data. And perhaps we as theoreticians should start addressing the question of how can we limit this amount of junk, which we see all the time. Every time I go in a restaurant, I see two beautiful people sitting beside each other, and there they are. Cell phones. And you hope they're texting to each other. But unfortunately, you think that they're probably not. Is there any theoretical basis for looking at that problem?
It's called TMI, too much information.
Or Mike, you want to comment?
It's your fault, Bob. You're the one who invented this technology that allows them to text each other. Sorry, sir. It's your fault.
All of us here, we share the advice.
I would follow up on that and say that information is not the same as bits, right? And I think there's many interesting theoretical problems on how do we extract the real information from all the junk to do what we want to do. I think that's also where learning comes in and decision systems come in. So I would say that there are, at least the problem can be posed. Are there theoretical solutions to that?
I think that was the whole point about X. Like, did you really want X? No, you probably wanted some function of X, which was, presumably highly surjective. So why are you sending all this junk versus just sending the bits that are just necessary for that function, which is not the same as computing the function and then sending the bits. I mean, I could have come up with that, It's actually, again, in these distributed settings, like the ones that Moore was talking about is, we all have data and you want to know something which is a highly surjective function of that data. How do we send it to you in a way which is as, as efficient as possible? And also going back to the question about security, also as secure as possible, because I'm only sending you what you need. So, because, a lot of security aspects right now is not just somebody breaking, my crypto system, but it's somebody finding out stuff about me incidentally because I accidentally revealed information which I didn't realize could lead to exploitation through machine learning techniques. So I think there's a lot of work on that, which is another aspect of security in that sense. But it was tongue-in-cheek about the X, but that's basically it. You probably don't want the X, and it's probably not even you don't want the X. You probably want a function of X1, X2, X3, and so on. At least that's my view of it.
I guess when Shannon split the semantics of data from the data itself, it was a huge simplification which allowed us to make lots of progress. But perhaps it's time to practice and put the semantics back in. I simply have no clue how to do this. So
basically we need LDPC codes which forbid texting, right?
That's right.
So there was another question, I think, yeah.
Thank you for your inspiring discussion. So in terms of transmission, I think data compression and feature extraction can be helpful for transfer information in one sense. On the other hand, the junk information, just like junk DNA or dark matter or dark energy, may have other functions. In terms of big data error, it can derive some hidden information inside of the data structures. That's my understanding.
Okay, maybe we have some networks questions. Are there any networks questions? Yeah. Yeah.
The problem of avoiding junk probably has to do with the realm of economics. Right now, the internet is free. The moment that sending information will cost you, junk will evaporate.
Okay, more good ideas for for forbidding texting. Of course.
They're junk.
It's gonna cost you.
So I think we will review the talks, and if we decide they're okay, then we'll post them. I'm just kidding. Yeah, they will be posted, right? Yeah. Okay. Any other questions from the audience? No, nobody? So I don't know, maybe we should discuss among ourselves then. So, I mean, I had this general...
I just wanted to comment about your crypto question. I mean, there is a lot of crypto work being done at MIT. It's just being done... Yeah, at MIT, just not in LIDS.
What I'm asking, why
You want to bring it into LIDS.
the big pie, why don't we, this is related,
I see.
you know, and now it's converging. I mean, I've become unemployed essentially by crypto because I was doing distributed system. These Santoshis that came essentially use crypto to solve my problem. And it became, everybody said, this is the future, and we put me in the past. I'm in the past.
Actually is a lot of very interesting work going on at the intersection among distributed storage, like the stuff that Mor was talking, coding, and encryption, right? So, you know, they're basically variants of, they would be sort of variants of the McLeish crypto system in effect. But there's quite a bit of work of that, and you know, many of us were at SIT this past summer in Paris. Al here, somewhere here, is one of the co-chairs. It was fantastic. But there was quite a bit on what they call post-quantum systems, which is really McLeish crypto systems. So the idea is that, you know, like the different, what's stored in different locations is kind of being used as a key to others. So you have these MDS codes, and you know, you'd have to have access to enough nodes in order to be able to reconstruct it. So I mean, you know, that's very much at the intersection of crypto and networking and coding. You know, to give you one example.
So another example, so at USC, we just renamed our group from the Communications Science Institute to Communications, Information, Learning, and Quantum, CILQ. And so to the extent where, you know, Quantum is working on the other side, trying to break the crypto.
But in general, I have a question about optimization. Because I was in an NSF panel, and there was a David Slater, I think, from Stanford, essentially saying, forget all this optimization. The capacity of the network is so big that all this queuing is not of interest to me. And it's really, my question is, if we didn't have sophisticated information theory and all this stuff, will we be in a different place today? It's the hardware that gives us all this huge and bound of leaps forward. It looks to me. I don't believe that some particular algorithm in information theory, that coding or whatever, that if we were missing it, we will be in big trouble today. And similarly, when I say this in my department, Leonard Kleinrock is in my department, and I told him, I think you made a mistake. You were at the early days of the internet. You chose to do the optimization, the routing, optimal routing, queuing, and all this stuff. Other people went and did TCP/IP. The glory was there. not in the optimization. So in general, I wonder how much optimization really adds the marginal addition.
So why didn't you put the L in front of the I and then it would have been click?
Yeah, we thought that was too much of a backronym.
I think Bob McAleese had given a talk vis-a-vis Shannon versus Newton.
Right.
Essentially asking how much of the advances in communications was due to the physicists and how much of it was due to the information theorists.
Yeah.
My biased recollection might be was that perhaps we were ahead, but does anyone remember it more accurately?
Yeah, I remember that. That was
I
same
see.
order.
Okay.
Yeah.
Or the same order. Okay,
Yeah.
fine. So.
Yeah.
Maybe 60-40 or something.
Just to explain, this was for the space communication, for the deep space, right? So there was advances in physics, not so much in computation, right? And then the advancement coming from the better codes, right? And the question was, what was better, the antenna design or the codes? And I think, there was slight advantage to antenna part, but roughly of the same order.
I guess another analogy is just, communication systems existed before Shannon, and for a long time they existed the same way, even after Shannon. So Shannon's results are fundamental and they give us much insight, but maybe those results really were a long time coming. So maybe it's the same thing with optimization. I mean, networks existed before all these cool optimization methods. And so we have these legacy systems, and it's maybe hard to change these things, but optimization gives us a lot of insight, not only into solving networks problems, which might end up really being implemented much better than the existing TCP methods in the future, but it also gives us intuition on how to optimize other things.
So I think we are approaching the last maybe couple of questions. So yeah, so is there somebody wanted? Okay, anyway, so then I'll ask a general question. I'm very curious in all these panel discussions to ask you guys from your long and stellar careers to share with us something along the lines that I think many of the junior or maybe senior researchers in the room experience, that there are moments where all of our colleagues or many of our colleagues run to do something, right? And all of them somehow join some recent trend, right? And I stay out of it or you stay out. And then you keep because you want to do your stuff, right? You're still interested in doing, you're still passionate about your stuff while everyone else is switching to doing something new. And then I'm sure this happened in the past to you, and I was curious, how did you feel about it after? Did it pan out as a good decision not to join them? Or maybe you joined them and this was the right decision? And I don't know, just maybe share some memories about this kind of events in the past. Anybody? Emre?
Okay. I think it takes a long time to learn a new subject, so life is too short. In other words, so personally, I stayed on one subject, and it's good to follow what's going on in other areas, to have a wider perspective, and to put your own work in the bigger picture, and to steer your own research in the right direction. But speaking personally, I found the subject that I'm working on extremely interesting, and communications theory will keep on being interesting. For those people, I tried to outline some of the challenges. So my personal choice has been to have a problem and pursue long-term interests rather than jumping from one subject to another.
So then you.
So for me, I am really interested in finding interesting problems. I'm problem-driven. I'm not tools-driven.
Bob?
Because I have faced that problem, I think, all my life. And my answer is when something else becomes hot, start to learn about it. Start to play with it. Keep playing with the things you're playing with. Play with both. When you get up in the morning, sometimes you really want to do one or you really want to do the other. And it's wise to do what you want to do. You do better work that way. And when you do that, every once in a while you change fields, but when you change fields, you're ready to do it and you plunge into it. It's like Shannon and what Shannon did. He always had these back burners where he had many problems that were sitting there. And when one of them became hot, he would play with it. He would go with it. Maybe he'd write something up about it, or maybe he just put it in a back drawer. But his way of operating was to do what was fun at the current time. And I think that's a good rule.
So Andrea, did you want to make a comment or? No? Oh, okay. Yeah.
Good strategy.
Saying you should do what you like. That basically sums it up.
Okay. Excellent. So I think with this, we should probably conclude this session. So the speakers are going to be around. You can catch them in the tomorrow and tonight as well. And I guess that's it for today, right? We're ending this. And let's thank the speakers again.